We already know how to describe motion along a single line, using position, velocity, and acceleration. But we live in a world of more than one dimension. A thrown ball arcs through a plane. The remarkable trick is this. We don't need new physics for two dimensions. We just need to split the motion in two. Here is the key idea. To handle motion in a plane, we treat each direction independently. Position, velocity, and acceleration are all vector quantities, and any vector can be resolved into components along two perpendicular axes. So we pick Cartesian axes, horizontal and vertical, with unit vectors I hat pointing along the horizontal and the j hat pointing along the vertical. Then the whole problem breaks into two ordinary one-dimensional problems, one for each axis. And the most important part, our definition of velocity as the derivative of position holds for each component separately. Whatever calculus we learned in one dimension, we simply apply it twice, once to the horizontal piece and once to the vertical piece. That is the entire strategy. Start with position. At any time t, the object sits somewhere in the plane, measured from a chosen origin. We write its position vector, r vector of t, as x of t times I hat, plus y of t times j hat. Read this carefully. X of t is the horizontal coordinate, the object's distance along the horizontal axis at that instant. Y of t is the vertical coordinate, its height. Each is a function of time because the object moves. I hat and j hat just point those two pieces in their proper directions. So the single position vector is nothing more than a horizontal coordinate and a vertical coordinate, bundled together with direction. Two numbers, evolving in time, completely pinned down where the object is. Now velocity. Velocity is the rate at which position changes, so the velocity vector is the time derivative of the position vector. And here the independence pays off. Differentiating r vector of t component by component, the velocity vector, v vector of t, equals the derivative of x with respect to t times I hat, plus the derivative of y with respect to t times j hat. We give these two pieces names. We define v sub x of t as the derivative of x with respect to t, the horizontal component of velocity. And we define v sub y of t as the derivative of y with respect to t, the vertical component of velocity. So the velocity vector is v sub x times I hat plus v sub y times j hat. Notice what happened. We never differentiated a vector as some exotic new object. We differentiated each coordinate function on its own, exactly the one-dimensional derivative we already know, and then reassembled the answer. Acceleration follows the very same pattern. Acceleration is the rate at which velocity changes, so the acceleration vector is the time derivative of the velocity vector. We differentiate again, component by component. The acceleration vector, a vector of t, equals the derivative of v sub x with respect to t times I hat, plus the derivative of v sub y with respect to t times j hat. And as before, we name the components. We define a sub x of t as the derivative of v sub x with respect to t, the horizontal component of acceleration. And we define a sub y of t as the derivative of v sub y with respect to t, the vertical component of acceleration. So the acceleration vector is a sub x times I hat plus a sub y times j hat. It is the identical move, one level up. Differentiate position to get velocity. Differentiate velocity to get acceleration. Each step done independently in the horizontal and the vertical. Step back and see the whole structure. We have one repeated idea applied twice. Position differentiates to velocity. Velocity differentiates to acceleration. And every one of those derivatives is taken component by component, the horizontal piece never mixing with the vertical piece. That independence is the deepest point here, and it is easy to underappreciate. The horizontal motion of a projectile does not know or care what the vertical motion is doing, and the vertical motion does not depend on the horizontal. They share only the clock. This is what lets us take a hard two-dimensional problem, like a ball flying under gravity, and solve it as two simple one-dimensional problems that we already understand, then stitch the answers back together with I hat and j hat. Master this single move, differentiate each component independently, and you have the full machinery for describing any motion in the plane. Next, we put it to work on a projectile. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.